Okay, so yesterday we learned how to graph rational functions, and let me just remind you, yesterday's notes looked like this. If we had a constant on top, then our vertical asymptote was going to come from this, if I set it equal to 0, and that's how we got x equals h. Our horizontal asymptote would be, if I ignore this, it would just be y equals k, and then we would graph it. And then we would make a table, we would center around the vertical asymptote, because that's where it was undefined, and then we would plug in 2 numbers before, 2 numbers after. Today, this is literally like what 4-2 is about. So if you want to go into Pearson, you can click on 4-2 and you'll see these type of examples. So we're going to do the same exact steps as before. Except you'll notice now that instead of having a constant on top, you have a linear over a linear term. So we have linear over linear. As opposed to yesterday that it was a over, or a constant over a linear. So the question is, how do we graph a rational function of this form? And is there more than one way to graph? And the answer is yes. You can graph it the exact same way as yesterday. And in order to do a different way of graphing, we can use yesterday's example. Let me see if I have it. Do I have it? I don't have it. I lost it. It's somewhere. Oh, I do have it. Yesterday, remember that on the back, we saw this idea that we can just do long division. And then you can start graphing this. And that was the sad face because it was like it didn't fit. So sad. Okay. So today, we're going to graph it again using the same steps as before, and then I'm going to show you how it would look like had you done long division and then done yesterday's method, which is the same exact method. Okay, so first notice that step 1, just like yesterday, is we're going to go ahead and find and graph all the asymptotes. So I'm going to say identify and graph the asymptotes. Remember, there are two. There's a vertical asymptote and there's a horizontal asymptote. Once you identify them, we're going to go ahead and graph them. So let me get my highlighter, and you can just be like, imagine that is one of them. Again, the vertical asymptote is going to come from the denominator. And so the vertical asymptote is when we set this equal to 0. If I subtract d and I divide by c, I end up getting that x equals negative d over c. So that is our vertical asymptote. Same thing as before, except yesterday there was no number in front, so you could just do like the opposite. However, for our horizontal asymptote, because it's not like this is a linear term, a constant, like just a with plus a number. Remember yesterday, we could just take this thing up here. Like this was our vertical asymptote. Today, what we're going to do is, if they have the same degree top and bottom, then the coefficients are going to be our horizontal asymptote. So my horizontal asymptote would be y equals a over c. And I'll keep doing that over and over again. Step 2, we're going to make a t-chart. And we're going to center it around the vertical asymptote. So again, and let me see, I can maybe fit it over here. So I can have x, and I'm going to plug it into the original again. And if you've been doing this method since yesterday, this will seem like a piece of cake. In the middle, remember, we put the x value, that vertical asymptote, that's going to turn this to be undefined. We would put that in the middle. Remember, this is our vertical asymptote. And then we would plug in 2 numbers before, 2 numbers that are less than that, and 2 numbers after, or 2 numbers that are more than that. And then because we would use the original function, then we're allowed to graph from the origin. Our domain will be x cannot equal, and again, it'll be same idea. It'll be the same shape. There will be 1 arm on that side, 1 arm on the other. The domain would be all real numbers except that vertical asymptote. So that would be negative c over d. And the range would be all the y values. It goes forever to the bottom, it goes forever to the top, but it doesn't hit that asymptote. So y cannot equal to a over c. You don't have to memorize these numbers, you just have to know the structure of it. Horizontal asymptote comes from a horizontal line. Vertical asymptote comes from a vertical line, and we're going to ignore end behavior. Okay, so for example 1, let's go ahead and actually do it. So first step, we're going to go ahead and find our vertical asymptote, and we're going to find our horizontal asymptote. Vertical asymptote comes from the denominator. If I set that equal to 0, I would get x equals 2. And then I go ahead and graph it. horizontal asymptote, because it is not an actual number. Hi. Give me a minute. Because this is not an actual number, we have to check if the degree is the same on both, then we could just take the coefficient, and that would be y equals 1. And then once we do that, we can graph it. Step 2, we're going to make a t-chart. And we're going to use the original function. And we're going to center it around the vertical asymptote. So pretty much in the middle is the one x value that makes this undefined. In this case, it happens to be 2. And remember, we don't want to be just centered around the origin. We want to be centered around where the action is happening. So I want 2 numbers before 2 and 2 numbers after 2. So that would be 0, 1, 2, 3, 4. And then we plug them in. So if I plug in 0, you get 0 over negative 2, which is 0. If I plug in 1, I get negative 1/2. If I plug in 3, I get 3. And if I plug in 4, that's 4 over 2, which is 2. We graph it, and because, again, this is the original function, we graph it from the origin. 0, 0, 1, negative 1/2. And this will be enough to go towards the asymptotes. 3, 3, and 4, 2. And this will be enough to go towards the asymptotes. Our domain, it goes forever to the left, forever to the right, but it doesn't hit that asymptote, so x cannot equal to 2. It goes forever down, forever up, but it doesn't cross that line of y equals 1. The horizontal asymptote is a horizontal line. The vertical asymptote is a vertical line. The x-intercept, I see it right there. It happens to be 0, 0, which is also the y-intercept. And for now, we're going to ignore the end behavior. Okay? So catch up. Okay, so now moving on to the next example. Again, we're going to start with the vertical asymptote. Vertical asymptote comes when you set that equal to 0. You get x equals 0 because you just divide by 2. Horizontal asymptote is going to be, if they have the same degree, top and bottom, then we just take the coefficients. So that will be y equals 1/2. So once we're ready, we go ahead and graph it. X equals 0 is a vertical line. Y equals 1/2 is a horizontal line. Then we go ahead and make step 2. We're going to make, by the way, I like to graph my asymptotes before I actually start plotting the points. Always graph the asymptotes before you put your points down. Step 2, oh man, that shouldn't have been, whatever. We're going to make a table around the original problem. And if I use the original problem, I have to really be careful about what I plug in. In this case, I want to know everything that happens before and after. So we just happen to be centered, but it's not always the case. So I use the original. Once I use it, I can graph from the origin. So I'm going to plug in the number in the middle that makes this function undefined, which in this case happens to be 0. Then I'm going to plug in 2 numbers before, 2 numbers after, and I plug them in. So that'll be, oh man, I need like a little, maybe I'll do it off to the side. Do I want to? Yes. Okay, so negative 5 over, because negative 2 minus 3 is negative 5, over negative 4, that's 1.25, or 5/4, or 1 1/4, or 1.25. If I plug in negative 1, I get negative 4 over negative 2, which is 2. If I plug in 1, we're going to get 1 minus 3, which is negative 2 over 2, which is negative 1. And if I plug in 2, I get negative 1 over 4. Right? 2 minus 3 is negative 1 over 4. So that's negative 1/4. So then I'm going to go from the origin, because I sketched using my original problem, I can graph from the origin. Left 2, up 1 1/4. Left 1, up 2. That looks legit. And then we go right 1, down 1. Right 2, down 1/4. And this looks pretty good too. Now our domain is all the possible x values. It goes forever to the left, it goes forever to the right, but it doesn't touch that asymptote, so x cannot equal to 0. It goes forever down, forever up, but it doesn't touch the horizontal asymptote, so y cannot equal to 1/2. Horizontal is y equals, vertical is x equals. X-intercepts, I know that this has to hit it, because if I approach that asymptote, then that means I have to hit the x-axis. So in order to find it, I can always plug in y is 0. So I'm going to do it off to the side. If I set y to be 0, I get x minus 3 over 2x. And really, if you want to make a fraction 0, you just have to make the numerator 0. But if you doubt it, you could just like cross multiply. You get x minus 3 equals 0. As long as the numerator is 0, the entire fraction is 0. And that's how we get 3 comma 0. So now I know it's going to hit 1, 2, 3. It's going to hit right there. The y-intercept, it doesn't have any. I can see it, and I also know that that's the where the vertical asymptote is at. But I can also verify, if I plug in 0 for x, I get 0 minus 3 over 0, which I'm not allowed to divide by 0. So then we say there is none. Catch up. Okay, so now let's move on to the back. Oh man, wait, is this pretty? This is not pretty. It bled through, so let me try this one. Okay, so to find the vertical asymptotes, remember, vertical asymptotes come from our denominator. Vertical is all about the x values. It's very similar to your domain, which also comes from your denominator, domain, denominator. So in this case, my vertical asymptote happens when the denominator is equal to 0, because you can't have a denominator of 0. So if I set the denominator equal to 0 to find the actual vertical asymptote, remember, the vertical asymptote would be x equals versus our domain, which would be x cannot equal. So if I do this, because it's a quadratic, I'm going to go ahead and factor it. And then we solve, and we see that whenever you don't have a linear, you may not end up having with one vertical asymptote. In this case, we have two vertical asymptotes. The vertical asymptote x equals negative 4 and x equals negative 3. Okay? I suggest that you maybe pause this and then graph it on decimals and see what it looks like. Okay? For the horizontal asymptote, I know that if it's a over x minus h plus k, then the horizontal asymptote ends up being y equals k. If it ends up being y equals ax plus b over cx plus d, the horizontal asymptote ends up being a over c. But what happens when they don't have the same degree and this is not a constant? So I'm going to go ahead and go over a couple of cases. And I'll keep revisiting these cases because these cases are a little crazy. Okay, so at the very bottom, I'm just going to make a quick note about horizontal asymptotes. Horizontal asymptotes. There's so many rules to them. Okay, so there's case number 1. So I'm going to call it case 1. Let's say the degree of the numerator happens to be less than the degree of the denominator. So that would look something like g of x equals x plus 4 over x squared plus 1, where the degree on the top happens to be smaller than the degree on the bottom. Then all I think about is, well, an asymptote is the value that you approach. So in all the instances, our horizontal asymptote, has been related to what do I approach as I go to the right and what do I approach as I go to the left. So as x gets really, really, really big, like as x goes to infinity, what value does he go to? And as x goes to negative infinity, what value does he go to? And whatever that value is on both ends, that is the horizontal asymptote. So in this case, if I just think of a really big x value, so I could think of as x gets bigger. And by bigger, I mean infinity. If I make x into a huge number, even though it'll be a huge number plus 4, on the bottom, it'll be a huge number squared plus 1. Okay, sorry. So if I think of a really, really big number, it'll be a big number over a big number squared, which means the bottom is going to grow a lot faster than the numerator. So that means I'm going to end up with like a relatively large number divided by a huge number, because the bottom will be like a squared of the numerator, kind of. But it'll be like not just twice as big, but itself times itself big. So you'll end up with a big number over an even bigger number. Oh my gosh, all these. Sorry, guys. So if I think of maybe having like one cookie divided by 1 billion people, how much cookie would they have? Hopefully you're thinking 0. So if I take a number and divide it by a huge number, this will become 0. If I take one cookie and divide it by 1 billion people, most likely they'll get 0 cookies. If I think of 100 cookies divided by 1 billion people, still going to be about 0 cookies. You get like crumbs. So in this case, whenever your denominator is bigger, then if your denominator is bigger, that means it's number divided by huge, which means this will be your horizontal asymptote. Case 2. And I'll keep going over it because it is a weird thing to think about. If your degree of your numerator is bigger than the degree of your denominator, something like x squared plus 1 over x plus 2. Now I see that the top is growing really, really, really quick. So now I'm thinking of the top being bigger over a not so big number. Well, in that case, if I have a billion cookies and I only divide it by 10 people, they're going to get a lot of cookies. So this is not actually going to approach a number. It's just going to keep getting bigger and bigger and bigger. So in this case, this is just going to equal to a big number. So big that, in fact, it's always going to be increasing. It's never actually going to approach anything. So this, we say, has no horizontal asymptote. In fact, it has a slant asymptote, but we'll talk about that later. Okay? But if the bottom is bigger, it's going to be 0. If the top is bigger, we're going to say it has no horizontal asymptote for now. And if the degree of the numerator and the denominator, so case 3, degree of numerator is equal to the degree of the denominator, like if I have y equals 2x plus 3 over 4x plus 5, if they're the exact same, then I could just take that, the coefficients, 1/2. So this is easy. These you just have to think about. So bottom bigger, it means you're dividing cookies by a lot of people, which means they'll get 0 cookies. If you have a lot of cookies divided by less people, you're never really going to have to run out of cookies at all. Okay? All right. So now moving on. So in this case, find the horizontal asymptote. So I'm thinking of a really big number. If I plug it in, I'm going to end up with number over number squared. Plus whatever. It's got more stuff. But I'm thinking of a number divided by a really big number. I'm thinking of 1 cookie divided by a ton of people, which means they're not going to get that many. So y equals 0. You can also double check it. Okay? All right, moving on. For the graph, in this case, for now we're going to try to stick to this, linear over linear. Whenever you have linear over linear, we are friends. Everything's nice. So, example 1. Well, step 1. Let's find the vertical asymptote and the horizontal asymptote. Vertical asymptote would be x equals, if I set this equal to 0, I'm going to end up with -4/3. If I set the, in order to find my horizontal, I could just take these, same degree, y equals 2/3. Oh, you can't even see it. Okay, sorry. So, I moved it, and I'm sorry. I didn't know you couldn't see. So you can now see, like, we already know that if I have number over x minus h, it's going to be y equals k. If I have the same degree, it'll be a over c. And after going over all those 3 cases, in this case, I end up with a bottom bigger number. The bigger number's on the bottom, so I have cookies divided by a lot of people, so they're going to get 0 cookies. Example 5. We have a linear over linear, which is nice. Yes, but I have to go. Okay. So now that you've caught up, we can go ahead and graph. Oh man, this is ugly. This is -1 1/3. Where did I get this problem from? Maybe Pearson. Ugh. And then 2/3. 2/3 is somewhere here. 2/3 of the way up. This is ugly, but it's okay. Step 2, we're going to make a t-chart. We're going to use the original function. And I'm going to plug in the vertical asymptote because that's what makes the function undefined. And I'm going to plug in 2 numbers before and 2 numbers after. Well, I guess this is really good. Because if I have -1 1/3, 2 numbers before would be something like -2, -3. And if I want 2 numbers after, it would be something like -1 and 0. Okay, and then I can plug in -3, which would be -6 plus 1 is -5. -9 plus 4 is -5, so this is 1. If I plug in -2, we would get -3 over -6 plus 4 is -2, so that's 1.5. If I plug in -1, it would be -2 plus 1, which is -1. -3 plus 4, which is 1, so that's -1. And if I plug in 0, I would get 1 over 4, or 0.25. So now I can go -3, 1, -2, 1.5. And that looks good. As long as I don't end up on opposite sides, I'm okay. For the other little one, I'm going to go -1, -1, and then 0, 1/4, positive 1/4, which is still good. Oh man, I'm cutting it close. The domain is going to be x cannot equal to -4/3, y cannot equal to 2/3, y equals 2/3, x equals -4/3. The x-intercept, it's happening somewhere here, like on the negative side. So to find it, I'm going to let y be 0, which means 0 equals 2x plus 1 over 3x plus 4. But really the denominator will cancel, so I just have to focus on the numerator, which ends up being -1/2. So 0, -0.5. And that makes sense that that would be around -0.5. For the y-intercept, I already found it. It was 0, 1/4. Or 0, 0.25. And we don't have to do end behavior. Oh, yay, we did it. Okay, so just to close off, you can try to catch up. That says -4 over 3. I hope, I think. No. What does that say? Yeah, -4 over 3. I got it from there. Vertical asymptote. Okay, so just to kind of close it off, on the front, there is another way you can graph all of these, but it's more work. But I just want you to realize that we did the same thing. When it's linear over linear, the bottom is our vertical asymptote. The coefficients divided, the ratio of the coefficients is going to be our horizontal asymptote, and then we make a table. However, in yesterday's notes, we also learned that I could have just, if I want to rewrite this to look like yesterday's notes, I could just use long division. In and out, in and out. So this is x plus 0, this is x minus 2. I multiply it by 1, I get x minus 2, switch, 2. So g of x can equal to 1 plus 2 over x minus 2. And you can still see that the vertical asymptote would be x equals 2. And you can now see that the horizontal asymptote would be y equals 1, which is right there. So just letting you know that it's not that we're memorizing different things, it's just that different forms require different structures, different ways of finding the horizontal asymptote.